Uh, Hello all. Uh, in this course which I have designed, it is a brief course on Introduction to Photonics. And in this course, I'll discuss all the important thing which is in photonics and its applications in today's era. So before we go deep into the course, I'd like to introduce myself. Myself is Jagyansis Jena, and I am an MTech student in electrical engineering at IIT Madras. And before that, I have a MSc Physics degree from NIT Rourkela. So this course is being it is a part of evaluation of EE5500 course which is provided by Electrical Engineering Department of IIT Madras, and the course name is Introduction to Photonics. So let us go deep into this course. So before going deep into the course, the question arises: why photonics? Why should we read photonics? So there are many applications of photonics in this era. The photonics is known as the new electronics, the electronics of this 21st generation, or it will replace electronics in next 2-3 decades. Why is that? Because by the laws of physics is kind of limiting the application of the electronics. We can't shrink the chips and the memory devices. We can't make it smaller, more smaller, and that's what it is important. We have to make the devices as small as possible, and that's why they are become affordable and more useful. So the problem is that the quantum tunneling effect affects the miniaturization of these electronic devices. That's where the application of the photonics start. So here I have listed some basic applications of the photonics. So the first application is energy from solar panels, right? So as you can see that I have included a photo of the solar panels here. So solar panels act on basic principle of photodiode or photodetector. So what happens in this is that when the solar energy falls on this solar panels, it creates a electron and hole pair, and that electron and hole pair constitute a current which is known as photocurrent, and that leads to creation of energy, right? So now phone camera is, of course, the camera is based on photonics. So in every smartphone we use every moment we capture that is an application of photonics. And biomedical and healthcare is there is applications of photonics because by using fluorescence spectroscopy we identify the cancer cells, and for gastric related problems we use the endoscopy method which is based on this photonics applications. And fiber optic communication, this is one of the most important application of of photonics, because in fiber optic communication the loss is very low, the data loss is very low, and because of this it already fiber optic communication has fiber optic cables already replaced copper cables. That's why most of you know about geo fiber and every fiber. So fiber optic communication is a revolution. It is going on. It will be more revolutionized in next 2 or 3 decades. And of course, space technology. We take the photos we use this type of drones in space. We use different type of spectroscopy, absorption spectroscopy, emission spectroscopy. You use that to study the soil structure, and we in also in telescopes also we used to analyze the spectra of different galaxy, different stars to know its constituents, right? So that's why photonics is very important to study, and it is a new science. It is a new science with many applications, which is coming in this, which is very applicable in this era. So let's go to the next. So the topics we discuss in this brief course is first is we will discuss the ray optics, and then we will jump to wave optics, which is the broader version of ray optics, and it incorporate more theory about or study of photonics. Then electromagnetic optics. After that, we'll go to the quantum optics, which is one of the newest theory of newest optical theory. And then we'll discuss about lasers and photodetectors. These are very important topics. And after that, nonlinear optics and what happens in nonlinear optics. We'll discuss these things in detail, and we'll know the difference between linear and nonlinear optics. We'll discuss what is ray optics in detail, wave optics in detail, electromagnetic optics in details, and we'll find out the drawbacks and the advantages of each theory of this of light. Now let us go to the next slide. So basically this is the first side of ray optics. So when a light wave propagates through and around objects whose dimensions are much greater than the wavelength of light, that's where the ray optics comes to, the ray optics theory holds that when the light waves propagate through and around the objects whose dimensions are much greater than the wavelength of the light, means like the lenses you use and the different optical devices, like big optical devices which use generally to light is generally reflected, refracted. These are basically the domain of the ray optics. The ray optics is also known as the geometrical optics. In ray optics, light is described by the rays that travel in different optical media by set of geometrical rules. So ray optics is defined by the set of geometrical rules, and the two basic laws, as we know from class 11 and 12, the law of reflection and the law of diffraction in ray optics. So this is basically a converging lens I have so here. So it is converging the light at this point. So So, as we discussed in the previous slide, that the two basic laws are law of reflection and law of diffraction. So, if we first discuss law of reflection, when light undergoes reflection, the reflected, the transmitted ray, and the normal lie on same plane. So, this is the first point we have to learn about the law of reflection. That if you see this plane, this diagram here, I have incorporated. This is known as the plane of incidence, right? So, as you can see that this is the incident light. So this is the incident light which is coming, and it is getting reflected at angle theta dash, and there is a if we draw the normal, so this reflected ray is normal and this incident ray, both means three of them lies on the plane of incidence, and then we can say that they lie on the same plane. Now the second thing is that the most important thing, the angle of incidence is always equal to the angle of reflection. So here theta, that the angle theta will be equal to theta dash. So that is basically the law of reflection, and it is always valid, theta equal to theta dash. Now if we discuss the second law, that which is known as the law of refraction. So there are few points you should know about the law of refraction, that at boundary between two media of refractive index n1 and n2, the incident ray split into two, a reflected ray and a refracted ray, or known as the transmitted ray. So here we have the diagram of this. So in the previous, the same diagram, we have shown only the reflected ray, but as we are discussing about going more detail, so I have means basically drawn three of the rays: the incident ray, and the reflected ray, and the refracted ray. So this is the normal. This is theta 1, and as we have already discussed, theta 1 will be equal to theta dash, or theta equal to theta dash. So the law of reflection, the angle of incident is equal to the angle of reflected, and the angle of refracted will be different. It will be theta 2, right? The relation between theta and theta 2 is given by Snell's law, which is given as n1 sin theta 1 equal to n2 sin theta 2. And here the point is the reflected ray obeys the law of reflection. The refracted ray obeys the law of refraction. The refracted, and the important point here is the refracted ray also lies on the plane of incident, or it is on the same plane as incident, reflected, and refracted ray. So here are 3 points. The important points are that they split into two types of the incident ray, split into two type of rays. One is reflected ray and another is refracted ray. First, the reflected ray obeys the law of reflection. The refracted ray obeys the law of refraction. and the refracted ray obeys Snell's law, which is given as n1 sin theta 1 equal to n2 sin theta 2. These laws, the law of reflection, the law of refraction comes from, if means it can be derived from the boundary condition principles. If we apply boundary condition, it can be easily derivable, but we should not go much deeper into that. So this figure we have already discussed, and in this figure it is, I have shown that this is water N2 is 1.33. Air is always taken as N1 equal to 1, and this is the normal line. So when incident ray is falling at 40 degree, and when the light rays goes from uh, means rarer to denser medium, it bends towards the normal. So theta, it will be theta, and theta we can find out by applying n1 sin theta 1 equal to n2 sin theta 2. So in this slide, I have listed some simple optical components which is used in ray optics most of the time. The first one is the uh, plane mirror. So the plane mirror, as you can see in this figure, that in plane mirrors we use as generally used for grooming purpose, and the distance of the object from the mirror is equal to the distance of the image from the mirror. The parabolic mirrors are what as parabolic reflector, and um, it can be the parabolic mirrors are also used in telescope because of its converging properties. We want all the lights which are falling on this telescope to be converged at this point, right? So that this transmitter can transmit all the information of that light rays to the computer which you are using to observe that spectra. So that's why we use parabolic mirrors. As you can see, in general, you can see that when you use different antennas, dish TV and Tara Sky antennas, they are also in the same shape as like these telescopes. And the third one is I have listed here is the elliptical mirrors. Elliptical mirrors are run by the Hero's principle, means the light rays if passes through one means if this is ellipse, let me draw it. It's a rough diagram of ellipse, and there are two foci of ellipse. So if a light rays passes through one foci, it will definitely by reflections goes through it will go through the another foci by Hero's principle, and this property is used for coupling of light. So you can use the coupling of light means into in fibers. You have to couple the light for better transmission, and that's where the elliptical mirrors can be used. And last but not the least, there are spherical mirrors. So spherical mirrors are used as concave mirror, convex mirror. So they the concave mirror are used by the dentist, and the convex mirror, you know that it is used as the rear view mirror, and there is always a sign in that the objects in the mirror are closer than the appear. So these are the basic simple optical components in the ray optics. As I have mentioned in previous few slides on the initial side, that fiber optic communication, the fiber optics cable are very important applications of photonics, and it has very low loss, and uh, it is used, it is replaced copper cables for data communication a long time ago because of its low loss. So let us analyze how these cables are made. So an optical fiber is a cylindrical waveguide. So it is a cylindrical waveguide, as you can see in this figure. This is a cylindrical waveguide and made of low loss materials. Low loss materials is important because we don't want our data to be lost during transmission. Such as silica glass is a low loss material. It has a central core. This is the core, central core, and it has a radius A, where the light is guided. So in core, the light is guided and embedded in an outer cladding. So this is outer cladding basically. So outer cladding has if the core has a refracting index of n1, the outer cladding whose radius is b is have an refracting index of n2, which is slightly lower than the core. This is how cylindrical waveguide is made, because the core has the high refracting index and the cladding has the lower refracting index. And as I have mentioned that the glass fiber is the remarkable technology has a low loss of 0.15 dB per kilometer. That's very important, and that's the reason why it is replaced copper cables. So in this figure, he's Charles Cow, and he has won Nobel Prize in because of this for his pioneering work on fiber optic communication. In fiber optic communication, the most important phenomenon which is used in fiber optic communication is total internal reflection. And in this slide, we'll discuss more about this. So I have incorporated a figure in this slide. So as you can see, that there are rays which are coming from denser side, and it is reflected on the boundary N1 and N2, and some of the lights are getting refracted, or we can say transmitted back, transmitted into the uh, rarer medium, and there is an angle theta c here which is mentioned, and at that angle the light ray is basically perpendicular to the normal. And if and there is a third kind of ray also mentioned here, that if the angle is theta greater than theta c, it is reflected back to the same medium. So let us go deep into what is total internal reflection. The critical angle between two boundaries is defined as the incident angle at which the angle of refraction will be 90 degrees to the normal. So what basically means in layman terms, that theta c is the angle where the refracted ray will be perpendicular to the normal. So basically what will happen, n1 sin theta c will be equal to n2 sin pi by 2, or we can say that n1 sin theta c will be equal to n2, or but the value of theta c, the value of critical angle for a boundary between n1 and n2 is given by theta c equal to sine inverse of n2 by n1. So the second point is, when the angle of incidence is greater than the critical angle, the light undergoes reflection at the boundary rather than refraction, and this phenomenon is called as total internal reflection, and it is used in fiber optics because we want our light to be guided in that optical fiber. We don't want our light to be transmitted back to the cladding, and that if the light is transmitted into cladding, that will be lost. So basically, in optical fiber, we use we couple the light in such a manner that it will always undergo total internal reflection and will not be transmitted into the clad. So as I have mentioned in the previous slide, that we have to couple the light in such a way that it will not be transmitted into the uh, cladding. So that factor, that how it will not be we do not undergo any loss, and the light will not be transmitted into the cladding part. So that's why there are two important things we have to make in. You have to note that there is one is numerical aperture, and other one is the acceptance angle. So what is basically numerical, the numerical aperture and acceptance angle? These are the factors which comes to play while coupling the light. The acceptance angle of a fiber is determined by the cone of external rays that are guided by the fiber. Means the acceptance cone is the cone in which uh, we have to couple the light in that cone so that it will be guided. It will be guided means it will go the total internal reflection, and that the numerical aperture is given by the sine of the theta. So that the numerical aperture is basically is defined at na equal to n1 square minus n2 square, and theta a, the acceptance angle, is given by sine inverse of numerical aperture. So if there is large na, more light can be coupled, and the light is transferred in many modes. And if there is small numerical aperture, there are few modes are possible, and the in small na, it is important that the intermodal dispersion is also not much in small numerical aperture, and on the basis of this numerical aperture, the fiber optic cable are divided into single mode fiber or multi mode fiber or few mode fibers. There is a classification in fiber optics about that. In this slide, we can see there is a graph between attenuation coefficient alpha, which is in which units is in dB per kilometer, and wavelength in micrometer. So this graph is very important because it gives an idea about the wavelength which should be transmitted in the optical fiber so that the loss will be low. So as you can see that there is relay scattering here around 0.8 micrometer to 1 micrometer, and there is if we go below there, there is also UV absorption band, and there is, we can see that at 1.3 micrometer at this point there is a local minimum is here, right? So the attenuation, as the attenuation is one thing to remember, that the attenuation coefficient is directly proportional to loss. The more is the attenuation, the more will be the loss. As you know, that will be, it is proportional to e to the power minus alpha z is kind of term we'll see in our means electric field terms, and for power it will be, if P transmitted will be around P naught into e to the power minus 2 alpha z, minus 2 alpha z. So z is the distance covered by means if the wave travels a certain distance z, this will be the loss e to the power minus 2 alpha z terms. So that's why attenuation is directly means affects the means power of the signal we're transmitting, and we want this attenuation to be minimum so that our loss will be minimum. So this at 1.3 micrometer we can see there is a local minimum. And one of the most important thing to notice that at 1.5 micrometer, nearly 1.5, we can say that it is really nearly 1.55 micrometer. There's a global minimum. So as you have already mentioned several times, this is around 0.15 dB per kilometer. dB per kilometer. So that is the ideal range for the transmission of in fiber optics, that our light wavelength should be along should be nearly around 1.50 to 1.55 micrometer, or it can be transmitted in the range of 1.3 to 1.55 depending upon how much loss we can bear, or we can stand in our transmission. So this graph is very important. Now let us go to the next slide. So, as I have mentioned that about SMF, MMF, means single mode fiber and multi mode fiber. So, what factors determine this means a single mode fiber or a multi mode fiber? What is the difference between these two? So, in single mode fiber, there is only one mode possible. Means there will be only one path to the light, and multi mode fiber there will be many paths or many ways to for the propagation of the light. That is the basic difference between the single mode and multi mode. And a light will be single moded or multi moded. It will be defined by the fiber B parameter, and it is given by 2 pi into a into numerical aperture. As you know, numerical aperture is n1 square minus n2 square root over by lambda naught. Lambda naught is the wavelength of the light we are transmitting. So basically, we can say that the most important factor we have to means keep in mind that that the fiber wave parameter which decides the light is single mode fiber or multi mode fiber depends not only on numerical aperture but also on the wavelength. So while we are saying that a light will be single mode or multi mode fiber, we have to specify in which wavelength we are talking about. So V is given by 2 pi A into numerical aperture by lambda naught, and for single mode fiber will have V parameter is less than 2.405. This point is very important. And for very large number of means if V is very large, the number of modes can be given by the formula m equal to 4V square by pi square. So this is the graph that means which determines this. Below this is single mode, and after that this will be multi-mode fibers, right? So this point is 2.405, and there is basically the mode, there are mode names like LP 01 mode, LP11 mode. So these are the basically cylindrical waveguide modes at which the light ray can travel. So so this is basically the most important thing we want to discuss in the ray optics, the most fiber optics, optical components, law of reflection and refraction. So in the next next slides, this is basically the end of the topic ray optics. We'll go to the much broader topic which is known as wave optics. Then electromagnetic optics and quantum optics will follow up after that. So this is the beginning of our second unit, which is wave optics. So the ray optics theory is useful if the light waves propagate through and around the objects whose dimensions are much greater than the wavelength. So in the beginning, we studied that this is the condition for ray optics to be applicable. In wave optics, we try to explain the phenomena when light propagates around a dimension which is comparable to the wavelength of the light. Means different molecules. Means when light propagates around sharp edges, different molecules which are comparable to the wavelength of light. So how the light behaves. In that case, we cannot apply the ray optics. So you can say that the ray optics is a subset of wave optics. So as you can see in this figure, I have shown some figure. So there is basically slits, two slits, as you know, Young's double slit experiment. This is slit S1 and this is slit S2. And there is interference pattern of maximum minimum, which is we obtain in the screen. And there is an equation, wave equation. This is the wave equation: delta square u minus 1 by c square, the delta square u by delta t square equal to 0. So this is the basic equation of the wave optics. And in wave optics, the intensity is given by the amplitude, the amplitude square, and we can say that IR is given by UR square. So these few points are important in wave optics. Now, if we talk about the reflection and refraction in wave optics, so we show them by the wave vectors k1 and k2. So we can see that if this is boundary, the waves are traveling and getting reflected from uh, the uh, the reflecting surface and moving at a means the k2 vector. K2 vector is a new vector. Its modulus will be same as k1 vector, but its direction will be different. And theta 1 is equal to theta 2. And so the same is goes for the transmission of light, or we can say the refraction of light, that it is moving with normal with wave vector k1 and theta 1, and it is being refracted as k2 and theta 2. K2, and in this case, the difference between both of these cases, you have to mark that here k1 vector mod will be equal to k2 vector mod in reflection. But in this case, k1 is not equal to, means modulus of k1 is not equal to modulus of k2. That is the important factor we have to mark in these cases, because these two wave vectors are in the same medium, but these two wave vectors are in different medium. So in different medium, the wave vectors will be different. And as you know, C will be given by C naught by n, the refractive index, and lambda will be given by lambda naught by n. Frequency remains unchanged while moving from one medium to another medium. So the there are some phenomena which can be explained by the wave optics, but not by ray optics. These two phenomena are known as the interference and diffraction. So interference is basically when two light waves interfere with each other, or it can be seen as when two light waves interact with each other. That's where there will be a resultant light wave, and that's because of the interference. And the diffraction is bending of light is along the sharp edges, or you can say that along the molecules or dimensions which are comparable to the wavelength of light. These are basically two different two important applications of light, which is described by the wave optics. So in this slide, we are going deep into this. That is, there is a wave x I have shown here, and there is a wave y. And if there is a constructive interference, the amplitude will be higher or the intensity will be higher, and this is given as the resultant wave. And if there is a destructive interference between these two, and the two rays will annihilate each other, and we will not get any resultant wave there. So in when the light beams interfere with each other, that we find out the patterns of constructive and destructive interference on the screen. So here I have shown this, that this is a slit, and one thing to remember that light undergoes diffraction and the interference at the same time. First, the diffraction is in single slit experiment. First, around the edges there will be diffraction, and after that, the light will be interfere with each other to constitute a pattern on the screen. So as you can see, this is the central maxima, and their subsequent maxima and minima is there. And in this figure, that here that there is a W is the slit width, and at Z, if Z there is a maxima is present at Z, then the law is basically W sin theta equal to n lambda. W sin theta is equal to the path difference between the two rays, and n lambda is for constructive interference. So the rays to be constructively interfere, this should satisfy W sin theta equal to n lambda, where W sin theta is the path difference and n lambda is the condition it should satisfy so that there will be constructive interference. So as you can see that how we have derived this, that the constructive interference and the destructive interference of the waves are dependent upon the phase difference between the waves. And how it is dependent is given by this equation, that when the two light waves interfere, the resultant intensity is given by u1 plus u2 mod whole square. It can be extended to u1 square plus u2 square plus u1 star u2 plus u1 u2 star. And then we transform this amplitude equation into intensity equation, that as I is proportional to, as I have mentioned earlier, I is proportional to u1 square. So u1 square is here I1, u2 square is equal to I2, and u1 u2 star and u2 star u1 is given by I equal to I1 plus I2 into 2 I1 I2 cos phi. So if the intensity of the two interfering waves equal to I1 equal to I2 equal to I0, so I is given by 2 I0 whole into 1 plus cos phi. This equation can be dissolved into this, and then we can see that 2 I0 1 plus cos phi can be extended to means 1 plus cos phi equal to 2 into cos square phi by 2, and then the whole equation will be 4 I0 cos square phi by 2. So depending upon the upon phi, I will be completely dependent upon the phase difference between the two waves, which is known as phi. And we can say that for while constructive interference, it will be 4 I0 means the extremum, and means the maximum we can say. And for destructive interference, it will be I equal to will be 0. So depending upon how much will be phi, we can say that the ray will under constructive interference or destructive interference. So in wave optics, an important thing, important application is that of interferometer. So interferometer's important goal is to create an interference of light. So how they create the interference of light is by manipulating light. So how the manipulation of light is takes place in an interferometer. They split the light by beam splitter, they reflect it by mirrors, and at last they interfere them. So in this wave optics, we will basically discuss about three type of interferometer: magenta interferometer. So in magenta interferometer, you can see this is one beam splitter, this is one mirror. So from beam splitter, the light is divided into two parts, and it is the one part is reflected by this mirror, and another part is reflected by this mirror, and at last they again go through another beam splitter, and then the two light rays which travel from two different paths undergo interference with each other. And the Michelson interferometer, it is one of the most used in laboratory experiments, and during laboratory experiments we obtain circular fringes by using Michelson interferometer. So in this Michelson interferometer, there is one beam splitter, and there is one mirror, and another two mirror. So by adjusting how interference takes place in interferometer, that by we adjust the so distance of the screen, the distance of the mirror, and we incorporate a path difference, so that due to the path difference there will be phase difference. So and due to the phase difference there will be an interference between the light rays which is traveling by two different paths. So this is path 1, this is path 2, and there will be a path difference between these two lights, and this path difference will lead to the phase difference, and due to the phase difference the interference, there will be interference pattern of maxima and minima. And this is Sagnac interferometer. In Sagnac interferometer there is one beam splitter. This is one beam splitter. These are three mirrors, and at last we can see U1 U2 is going in interference here. So one thing to mark here, that in magenta interferometer there are two beam splitter. This is one beam splitter. This is one beam splitter. In Michelson, there is one beam splitter and two mirrors. Here also in magenta there is two mirrors, right? But in Sagnac there is one beam splitter and three mirrors. So this is how we identify between magenta, Michelson, and Sagnac. And the basic laws of interference is also applicable here. I equal to I1 I2 2 I1 I2 root over into cos phi, or we can if I1 equal to I2 equal to I0, we can see I equal to 2 I0 1 plus cos phi. And this is basically the the graph between path difference. And as I have seen that the path difference is kind of the path difference incorporate a phase difference, and the phase difference gives rise to maximum and minimum. So in maxima there will be the intensity will be 4 I0, and for minima the intensity will be 0. So this is the graph basically. This is how we get the graph. So we discussed about the interferometers in detail in the previous slide, and in this slide we'll discuss about the application of interferometers. So the first one is optical coherence tomography, and it is the application of Michelson interferometer. So as you can see that there is a beam splitter here, and the second the eye acts as the one mirror, and from that there is also a detector here and mirror 2 here, and using this we detect from which layer of the eye the beam is getting reflected back, and we use an infrared light of 800 nanometer wavelength for this optical coherence tomography. In the Mass-Zehnder interferometer is used in thermo-optic switches, and we know the Sagnac is used for optical gyroscope. So gyroscope is a device which is a three-dimensional device, and it is used in battleships and helicopters for their orientation purpose. And in that the optical gyroscope for optical gyroscope applications we use the Sagnac interferometer, and for thermo-optic switches we use magenta interferometer, and for optical coherence tomography we use the Michelson interferometer. So these are basically basic use of interference parameters, and there are several others also, which is in lab we also use different type of interferometers to study the sample and its sample nature, and it is also used in space technology, because the interference of light has many applications, and where there is an importance of the interference, there will be an application of the interferometers. In previous slides, you have completed the wave optics part, and also before that, you have completed the ray optics part. In this few upcoming slides, we'll go into the detail of electromagnetic optics. So here I have drawn a picture of the electromagnetic wave, and this is in electromagnetic wave there is a magnetic field and electric field are perpendicular to each other, and it is shown by this yellow lines. Yellow vibrations are magnetic field, and the blue vibrations are electric field. Sorry, I have mentioned it may be wrong. The blue vibration here is magnetic field, and the yellow vibration are electric field. Now, in wave optics, we treat light as a scalar quantity. It's basically treated as a wave function, which is a function of time and space. So we can say that we mention this as psi xt in the wave optics part. The psi is the wave function, and we mention it as a function of x and t, space and time. The treatment led to shortcoming of wave optics. It cannot explain polarization of light. That's why the broader theory of electromagnetic optics is proposed. So polarization of light, as means the ray optics cannot explain interference and diffraction. Same shortcomings are with the wave optics, that it cannot explain polarization of light with scalar treatment. So electromagnetic optics is a vector theory in compromising of electric field and magnetic field that vary in time and space, and they are basically perpendicular to each other, right? So in electromagnetic optics, Maxwell equation describes a complete description of the electromagnetic optics. So, what is Maxwell equation? Maxwell proposed four equations, and these are that the first equation you can see that del dot d equal to rho. This is the differential form of the equation. There is also an integral form. We can see that we know the means everyone know the Gauss law in its integration form, that E dot ds equal to integration. That's its integral form. E dot ds equal to q upon s naught. And this is the differential form of the Gauss law, del dot d equal to rho. Where d is the electric displacement vector. This is the displacement vector, electric displacement vector. And the second, this is del dot d equal to rho. Rho is the q is the charge, and rho is the volume charge density. This is volume charge density. This rho is the volume charge density here. Now the second law is Gauss law of magnetism. It says that del dot b equal to 0. What does that mean? This is an important law, and it shows that magnetic monopoles doesn't exist. And if we write this in integral form, this will be b dot ds. B dot ds will be equal to 0. And the third law is known as the Faraday's law. That it is an important law because signifies the relationship between that electric field and magnetic field. That del cross E is given a minus of dB upon dt. So a changing means we can say that a changing magnetic field can produce an electric field. So basically, the means its significance, that if we go to its integral form, it is E dot dl equal to integration E dot dl equal to minus d phi upon dt. So this is basically a Faraday law, and in integral form, and phi is given by b b dot k. So excuse my handwriting here. B dot k. A is the area, B is the magnetic field. So basically, what it says, that a time varying magnetic field can produce an electric field. Same goes with the fourth law, that del cross H equal to del D upon del T plus J. So that means a time varying electric field also can produce a magnetic field. J is the current density, and D is the displacement vector, and the same goes for H. So this is Ampere-Maxwell law, and this is Faraday law. So these are the explanation of Maxwell equations, and the electromagnetic optics. The definition of electromagnetic optics is starts from these four equations. So these four equations are very important, and there are different forms of this depending upon which medium we are in. Is there a current in that medium? Is there charges in that medium? So depending upon that, these equations may change. So we have to take care of it, right? So these are very basic means equations, and everyone should remember this. Electromagnetic spectrum is basically the range of frequencies. So in electromagnetic wave, the frequency can vary from very less to means very high frequency, and depending upon the frequency or wavelength. Wavelength is inversely proportional to frequency, and by this we have divided in the electromagnetic means the range of frequency into several spectra, and depending upon that they have their own applications. So first is here that gamma ray. Gamma ray has a wavelength of 10 to the power 10 to the power minus 12. So it has a very less wavelength and high frequency. So here we can see that if there is less wavelength, that these waves are squeezed, but there means frequency is high. Frequency means as we know that C equal to frequency into lambda. So there is a if C is constant, if we take that C is constant, so lambda is inversely proportional to 1 by frequency, because electromagnetic waves move with 3 into 10 to the power 8 velocity in what in vacuum. So that lambda is inversely proportional to 1 by 8. So gamma ray is 10 to the power minus 12 meter, and the 10 to the power minus 12 10 meter is X-ray range. Ultraviolet is 10 to the power minus 8. Visible is 5 into 10 to the power minus 6. It is around 300 nanometer to 700 nanometer range, and that's the visible range. And infrared red is 10 to the power minus 5 meter. It's in meter. 5 into 10 to the power minus 6 in meters. So in nanometer, it will be around. The red wavelength is one of the important thing is the red wavelength is around 638 in nanometer. 638 nanometer. And the uh, other violet and the green wavelength are around that, means 30 nanometer, 500 nanometer. Everything is squeezed between that 350 to 700 nanometer. And after that, the microwave range is around 10 to the power minus 3 and sorry, 10 to the power minus 1 meter, and then radio wave is 10 to the power 3 meter. So radio wave has high wavelength and low frequency. So if we look at the applications, gamma rays are it has a high penetration power, and it is used in medicine for killing cancer cells. So we know that gamma ray therapy and chemotherapy, you can say something, they use gamma ray for targeted killing of cancer cells. Then X-ray is quite common. It is used in the view of inside bodies and objects. And ultraviolet ray it is absorbed by the skin and used in fluorescent tubes. And we are seeing the everything because of that visual spectrum. And infrared use in transmits it infrared use transmits heats from sun, fires, and radiators. And microwaves, microwave oven that used in cooking, radar, telephone, and other signals. And the radio wave is used for broadcasting. And why it is used for broadcasting, that is important, because radio wave has high wavelength. It is not affected by its different obstacles. So it is used for broadcast radio and television and also different satellite communication that they use radio waves. And so as you have mentioned, discussed earlier, that the polarization of light is described by the means electromagnetic optics, but it cannot be described by wave optics. So let us go deep into this polarization of light. What is basically polarization of light? And if we saw this slide, that the polarization of light is determined by movement of the electric field vector in space with respect to time. So how this electric field vector is moving? So in this case, we are saying that this is a linearly polarized light, and the electric field vector is moving in a linearized manner, and it is circular. We can see that this electric field vector is making a circle. So this is a circular polarized light. And also there is a classification in circularly polarized light. This should be left circularly polarized light, means the electric field vector is moving towards left with respect to the source, or it is moving towards right with respect to source. So that depending upon that, we describe them as left circularly polarized light or right circularly polarized light. And unpolarized light has means it is vibrating. The electric field vector is vibrating in every direction, so that's why it's called unpolarized light. And in linearly polarized light, it is vibrating in a linear fashion, and in circularly polarized light, the electric field moving in a circle. Electric field vector is vibrating in a circular manner with respect to the source. So the what determines the type of polarization? Phase difference determines the type of polarization. And here to how we will from phase difference, how we'll know is it linearly polarized, it is circularly polarized, or it is elliptical polarized. So I have mentioned this in this plane image. So for a plane wave propagating plus z direction, if E vector is given by ax ex into ay ey, e to the power j phi, this is the phase difference between the two waves, plus e to the power minus j k z. This term signifies that this is they are traveling in plus z direction. If phi is equal to 0, so that the phase difference between x component and ay components are 0, then this is linear polarization. First thing to mark. Second thing is phi equal to plus minus pi by 2. This is circular polarization, provided one thing we have to note, that if we saw the phase difference is equal to pi by 2, we should not conclude that this is circular polarization. So you have to know that it should be provided Ex should be equal to Ey. In that case, this will be circular polarization. Because circular in radius should be equal in circle, so Ex should be equal to Ey. And the last case means phi is not equal to 0, not equal to pi by 2, or Ex not equal to Ey. In that case, elliptical polarization means if Ex equal to not equal to Ey, then then it will be always means elliptical polarization, provided phi not equal to 0. And for any angle except this, means phi equal to means equal to pi by 4, phi equal to 3 pi by 4, phi equal to 62 degree, 71 degree, it will be always elliptical polarization. So it doesn't matter Ex equal to Ey or Ex not equal to Ey, it will be always elliptical polarization. So check for these two conditions. Basic, if we are given some equation and we have to find out that it is linear polarization or circular polarization or something else. So just check for these two conditions, and if these two conditions are not satisfied, then blindly go to the elliptical polarization, right? So in previous slide we have marked one thing, that first we have converted UPL, unpolarized light, to a linearly polarized light, and then linearly polarized light to circularly polarized light. So what we have used to go to that, how you are converting that conversion from UPL to PPL to CPL is given. It's done by this wave retarders. So what is wave retarder? Wave retarders affect the polarization of light by introducing a phase difference. A quarter wave retarder is used to convert linearly polarized wave into circularly polarized wave, and it introduces a phase difference of 90 degrees. So one thing remember, quarter wave retarder introduces a phase difference of 90 degrees, and a half wave retarder is used to rotate linearly polarized wave, and it introduces a phase difference of 180 degrees. So half wave introduce 180 degree uh, phase difference, and quarter wave introduce 90 degree phase difference. So here this is a linearly polarized light, and we give a phase difference of pi by 2, and as you have discussed earlier, that a phase difference of pi by 2 will incorporate a circularly polarized light. And again, this is a linearly polarized light, polarized in a particular direction. You will use means half wave plate here, and it is just reverse the polarization. So by 180 degree phase difference, it is just rotated that by 180 degree. Now it is already we have a CPL, circularly polarized light. We again add another quarter wave plate, which give a phase difference of pi by 2. So means there is also a pi by 2 phase difference here, and we are adding another pi by 2. So this is technically become pi phase difference. So that's why if the phase difference is pi, then linearly polarized light. And this is a half wave retardar which converting that a RCP, right-handed circularly polarized light, to LCP, left-handed circularly polarized light. So this is basically conclude the electromagnetic optics. In next few slides, we'll means as you have done ray optics, wave optics, and electromagnetic optics. So in this slides, next few slides we'll do the quantum optics. So what is the reason of bringing up quantum optics? So let us first study that. So electromagnetic optics provide the most complete treatment of light within the confines of classical optics. So this point is important, that we are confined until now we are confined under classical optics. But everything cannot be explained by classical optics. So certain optical phenomena are characterized by quantum mechanical in nature and cannot be explained classically. So these phenomena include absorption, emission, and photoelectric effect. So what exactly we are doing until now? That first, when we have studied the ray optics, it cannot explain interference and diffraction. So we go to the wave optics. Wave optics could not explain the polarization by its scalar theory. So we move to the electromagnetic optics, which is a broader one. Now we see another some explanations which could not be quantified under classical observations. So that's why we have to move to quantum mechanics. So these phenomena are described by quantum version of electromagnetic theory known as quantum electrodynamics, we can say also. And for optical phenomena, this theory is referred as quantum optics. So as you have seen that Albert Einstein is, everybody knows that a great scientist, E equal to mc square, and he won the Nobel Prize for photoelectric effect. And as you can see this figure, that there is a photocathode, the light is emitted, light is, means when light falls upon it, it creates the electrons. And the important factor here is that the means black body spectrum. So in black body spectrum, also it is another phenomena which is described by quantum optics. So this figure, you can see that this is at t equal to 77 kilometer. There is this graph is basically spectral energy density versus frequency graph, and you can see that there is curves at t equal to different temperature. There is different curves, t equal to 77 Kelvin, t equal to 300 Kelvin, t equal to 1000 Kelvin, t equal to 6000 Kelvin. There are different curves. So basically, in quantum mechanics, the first thing we observed, that we explained, is the blackbody radiation spectrum. After that, then photoelectric effects, absorption, emission. These things are only can be described by quantum optics. So, from quantum perspective, light consists of a particle called photons. A photon carries electromagnetic energy and momentum. So this point is important. These few points. Light, first point is from quantum perspective. Light consists of particle called photons, and a photon carries electromagnetic energy and its momentum, as well as its intrinsic angular momentum known as spin, associated with its polarization properties, and it can also carry the orbital angular momentum. So basically, everything is in quantum perspective is described by these photons, and it carries everything: the energy, the momentum, the spin, and the polarization properties, the orbital angular momentum. So everything is quantified by these photons. The photon has zero rest mass, and it travels at a speed of light in vacuum c. Means the speed of the photon in vacuum is c, and its speed in matter is reduced to v less than c, because we know v is given by c divided by n. N is the refractive index of the medium, and that's why v is reduced. And if you talk about the energy, equal to h nu, and it can be also nu can be also known as converted to c by lambda, or equal to c by lambda. These two formulas are very important. We should remember this. And E, the photon energy in electron volt, is given by, if you simplify this Sc, this will be this formula will be simplified to this one. So E in electron volt is given by 1.24 divided by lambda in micrometer. So in this figure, we can say that the polarization of these photons, that this is the X polarized photon and this is the RCP, right-handed circularly polarized photon. So these are basically the photon properties. So as we have discussed that in quantum optics, we can describe some phenomenon like absorption, emission, spontaneous emission, and stimulated emission. So let us discuss this three phenomena using these figures. So when a photon has energy level which is near the band gap or energy difference between two levels, this type of interaction is generally possible. So we are only interested in the photon which has energy level which is near to the band gap. So this is this is the band gap between two levels. So this is level 1 and this is level 2. So there are, if we are incidenting photons in this, this is, let us take this as a metal with a band gap of some uh, some x electron volt, and there is a number of number of photons which is which is being incident on this metal, and we are interested on only on this photons which has energy very close to this x electron volt. So in that case, three forms of interaction are possible: absorption, spontaneous emission, and stimulated emission. So what is absorption? Absorption is that the photon is absorbed and the electron or the ions are travel from level 1 to level 2, where level 1 can be ground state or any energy level, and level 2 is the higher energy state. So this is absorption, that this photon is absorbed and the electrons migrate from level 1 to level 2, or the ions migrate from level 1 to level 2. The another one is spontaneous emission. So in spontaneous emission, no, there is means there is a electron or ions in, or electrons or ions in level 2, and it is spontaneously emitted. It is spontaneously emitted means that the electron is migrated to level 1 and without any stimulation, and in this one, there is a emission. The it while means a photon is released and its frequency is given by h nu, and which is equal to the band gap. So this is the emission, spontaneous emission. This part, this is the spontaneous emission. Spontaneous emission. This one is spontaneous emission, and this the third figure is the stimulated emission. In stimulated emission, what we have basically doing is we are stimulating this electron to migrate from level 2 to level 1, and in that means while being stimulated, it exactly releases and clone photon, another clone photon, which value is same, which frequency is same as the incident photon, and two photons are released. So basically, this stimulated emission is very important with respect to laser. So in what if we recap this, what is the phenomenon we're seeing in absorption? That electron is absorbing a photon and migrating from level 1 to level 2. In spontaneous emission, there is no stimulation and just electron or ion which migrate from level 2 to level 1 without anything, and in that process it releases a photon of h nu energy, and in stimulated emission, a photon, incident photon, excites the molecule and it emits a clone photon which has same properties as the incident photon, and at the end we have two photons which is being released from the by this stimulated emission phenomenon. In the beginning of the photonics lecture, we have studied why we should study photonics, and in that point we have said that the application of photonics include the detection of cancer cells. So basically, the undermined formula, which is the fluorescence is the property which is used for detection of these cancer cells. So what is basically fluorescence? It is a phenomenon by which material absorbs light at a particular wavelength and emits out light at another wavelength. So what basically is we are if you saw this figure. So the absorption, this is the absorption spectrum, that at particular lower wavelength the uh, material is absorbing light, and at a high it is emitting at a higher wavelength. So some examples of this material which slow fluorescence is chlorophyll, rhodamine, cyanine, fluorescent carbon nanoparticles. So basically, if in this left figure we have described, means I have described the how this fluorescence is uh, what is the basic properties of the fluorescence and the working principles of the fluorescence. So basically, this is ground state and this is excited state, and the energy, as you know, the low energy in ground state and higher energy in this excited state. So an incident photon having lambda of energy incident on this uh, metal or anything on this fluorescence object which has this band gap, and absorption takes place. So absorption takes place from ground state to the higher excited state. So at this is step one, the absorption. And in the step 2, the at excited state, the electron undergo a non-radiative decay. This is known as non-radiative. Non-radiative decay means there is no radiation of photons or anything else, gamma rays, while moving from this moving in between this excited state. So the higher excited state has three levels. So it is moving from one excited state to the another excited state by non-radiative decay. And after that, there is an emission of means the emission of photon, which has a different frequency, lambda c you can see, and this phenomenon is basically fluorescence. So what exactly here we have the working principle of the fluorescence. First thing is that the photon, an incident photon is absorbed, and the electron migrates from ground state to the excited state. So this is basically absorption. Absorption takes place at lower wavelength or higher energy. Then there is a non-radiative decay, and in non-radiative decay we are losing energy. So we are moving from higher excited state to lower excited state, and then there is a emission in which another photon having higher wavelength is released. So this is basically the fluorescence phenomena, and chlorophyll, rhodamine are the cyanine. These are the examples of these fluorescence materials. So before going deep into lasers and uh, photodetectors and other important applications of photonics, we should know the difference between photon means metal, semiconductor, and insulators. So in metals, the valence band and the conduction bands are overlapping. In semiconductor, there is a band gap of 0.7 electron volt to few to means up to 1.1 electron volt in case of germanium. 0.7 electron volt band gap is there in case of silicon. So the band gap is lower than 2 electron volt in case of semiconductor, and in thermal excitation can also take the electron from valence band to the conduction band. And the insulator, the gap is more than 2 electron volt. So this is means you can say that in terms the insulator has a huge band gap, and the semiconductor has a mediocre band gap from in 0.7 electron volt in case of silicon, and 1.1 electron volt in case of germanium. And for metal they are overlapping. EF is the Fermi energy. So for semiconductor, EF lies between the conduction band and the valence band, and if we dope the semiconductor, this EF will change. The position will be closer to the conduction band or valence band, depending upon which we are doping, which type of dopant, that it's p-type semiconductor or n-type semiconductor. The another thing is the difference is the direct band gap and indirect band gap semiconductor. We should know about that. In direct band gap direct band gap semiconductor, this is that this is valence band, this is conduction band, and only by using photon we can the electron can observing photon a electron can move from the valence band to the conduction band. And this is the indirect band gap semiconductor. So we can see that this electron has to move with means these two conduction band and valence band are not directly means can be the electron cannot move from valence band to conduction band by just observing photon. So it has to observe photons and emit phonons while moving from valence band to the moving from valence band to the conduction band in case of the indirect band gap. So basically, what the examples of direct band gap and indirect band gap semiconductor, that indirect band gap semiconductor is the silicon. Uh, Silicon is the indirect band gap semiconductor, and gallium arsenide GaAs is the direct band gap semiconductor. So basically, the main difference between direct band gap and indirect band gap, in direct band gap there is only photon, and indirect band gap there with with photon absorption there is the emission of phonons. So this is the difference between direct band gap and indirect band gap, and metal semiconductor insulator. These are the basic difference on depending upon the band gap. So until now we have discussed this four optics from ray optics to quantum optics, and its the phenomenon which is described by them. Now we are going for one of application parts. The first part is laser. So what laser stand for? Laser stand for light amplification by stimulated emission of radiation, and laser works on stimulated emission of radiation. So this point is important. That's why we have taken time to uh, describe that stimulated emission. And to provide lasing action, laser requires a pumping mechanism. So a pumping mechanism is required for lasing action, and we'll go detail into this pumping mechanism. So that population inversion, which is a non-equilibrium state, can be achieved. So for laser, the population inversion is a state. We should remember this term population inversion is important, and that's why it's a pumping mechanism is provided to achieve this state. Along with that, a feedback mechanism also required to provide high gain. So basically, what we are doing uh, in this lasing case, that we are using a pump to gain population inversion, and we are using feedback mechanism for high gain. So what is the basic working mechanism of a laser? So first, what we do that we pump. This is the pump. By using the pump can we in the next slides will know the pump can be optical pump or electrical pump or chemical using chemical activity. We also can do the pump. So what basically the uh, goal of pumping is to pump from ground state to the short-lived excited state. So this is ground state. Then another stage is the longer lived excited state, and uh, the next level is short lived excited state. So from ground state we pump the electrons or ions to the short lived excited state, and there it goes a non-radiative decay, right? And after that uh, it undergo a emission and this emission is given rise to the lasing, and by stimulated emission. So this the first uh, as you have discussed that from the in stimulated emission, first we incident one photon and we get another clone photon, so there is basically two photons. Then these two photons will make four photons, and these four photons then will give rise to eight photons by stimulated emission. So there is a multiplication of this photons, and that give rise to the laser action or lasing action. So basically, if we recap, that's what is happening. We are giving a pump. we are migrating that electron or ion to shortly excited state, and that is where it undergo a non-radiative decay to a longer-lived excited state. And this part there will be many electrons in this metastable state. The longer-lived excited state is also known as the metastable state. So there will be more ions and electrons in this longer-lived excited state, and this and by stimulated emission, the two photons will be multiplied to 4, then 4 to 8, 8 to 12, 8 to 16, and by this the lasing action takes place. So this basically is a figure of the first laser, which is the ruby laser, and in this we can see a power supply, a reflective cylinder, a ruby rod, and there are two mirrors which is used for used as means for reflecting the means the photons which is means which is created by the stimulated emission, and this 100% one is 100% reflective mirror and another is 95% reflective mirror, and this the work of these mirrors is to provide a feedback mechanism, and there is a high intensity flash lamp, and it is used for optical pumping, and this 95% reflective mirror, the 5% of the energy is used as a laser beam. So this is basically trigger electron switch, and these are basically the components of the first ruby laser. So in the previous slide, the laser, we discussed about the laser pumping. So the pumping may be achieved optically using a flash lamp. We have seen that in ruby laser we are using a flash lamp, or electrically through a gas or gas discharge or an electron beam or ion beam. So we can say that this is flash lamps, optical pumping, gas discharge, or we can use a ion beam using cathode and anode. That means by means of injected charge carriers, we can do the electrical pumping, or chemically by flame or via chemical reaction that leaves the product in the excited state. So these are the means of providing energy, and this can be done by three important way: optically, electrically, and via chemically. So in laser there are two level of pumping system. One is 3 level, another is 4 level. So in 3 level, as you can see in the left side figure, there is ground state, there is short lived state, there is long lived state. So there is pump from ground state to the short lived state, and there is a rapid non-radiative decay, and its lifetime is given by tau 3 2. And the lasing is from this long lived state to the ground state. And the example is EDFA. EDFA we pump by 980 nanometer pump, and then from it is from ground to level 3, and then there is a non-radiative decay from this is I11 by 2 to I3 by 2, and the lasing is the lasing action is given the result of 1.55 micrometer laser we get by the lasing, and it is the lasing begins from 2 to 1 level. And in four level mechanism, there are four levels. One is ground state, one is ground level, short lived level, long lived level, and another short lived level. So the pump is from ground level to the short lived level, third short lived level. There is a rapid decay, non-radiative decay, and the lasing is from level 2 to level 1. And there is another rapid decay, non-radiative decay from level 1 to the zero ground state. So what basically difference between these two, that there is one non-radiative decay, and in this case there is two non-radiative decay. This is one non-radiative decay for 3 and 4 level pumping. And the example is this ND plus YBO for laser. The pump is from for I in 9 by 2 to 4 F5 by 2, then non-radiative decay to 4F3 by 2, and these two levels are basically very close, so we can treat them as one, and the lasing gives the 1.064 micrometer laser. So this is basically the difference between 3-level and 4-level mechanism. In the last slide, we discussed about the 3-level and 4-level laser system, and in this slide we will discuss about the semiconductor optoelectronics devices. So basically these are the few points I have listed here. So optoelectronic devices are the new generation devices. So in photonics we try to control the flow of photon, and in electronics we try to control the flow of charge carriers like electrons and holes. And in semiconductor optoelectronic device fabrication, these two technology are joined together. So we are basically what we are doing, we are adding the electronics and photonics together to come up with a new device which are called optoelectronic devices. Semiconductor optoelectronic devices serve as photon sources like light emitting diodes, laser diodes, amplifiers, detectors, waveguides, modulators, sensors, and nonlinear optical elements. These are the uh, applications of these devices. The absorption of photon can create an electron hole pair. Mobile charge carriers resulting from the absorption of photon alter the electrical properties of the semiconductor. And the recombination of an electron and hole can result in emission of photon. So why these two technology are joined together? Because the absorption of photon can create an electron hole pair. So these electron and hole pair are used in electronics, and the recombination of electron and hole pair can result in emission of photon. So in LED, the first applications are LED and laser diode. So as you have mentioned before, the recombination of an electron and hole can result in the emission of photon. This process is responsible for operation of semiconductor photon sources. So if a spontaneous radiative electron hole recombination give rise to photon generation in light emitting diode. So what basically happens in light emitting LED? So a spontaneous radiative electron and hole recombination gave rise to a photon generation. So what happens? So an electron in conduction band jumps to the valence band, and it is this as you have discussed three properties like absorption, spontaneous emission, and stimulated emission. So in this case, there is a spontaneous emission of a photon, and this is the working this spontaneous emission, the recombination of electron and hole, which is spontaneous in nature to give rise to a photon, is the working principle of LED. And the stimulated electron and hole recombination is responsible for generation of photons in laser diodes. So in laser diodes, we do have a feedback mechanism, and what we do is we stimulate the recombination of electron and hole, and in that case the photons we are generating, that is the basic principle of laser diode. So in laser diode, we know laser term is here. So if the laser term is here, there is stimulated emission. So here is the example of generation and recombination. So when an electron jumps from the conduction band to valence band, that leads to the recombination. And when an electron jumps from this valence band to the conduction band, it leads to generation of that means the generation of an electron and hole pair by adding a photon. When a photon incident on it, it leads to the generation of an electron and hole pair. It means it excites a electron from valence band to the conduction band. So after LED and laser diode, photodetector is another application of optoelectronic devices. So a photodetector is a device that measures photon flux or optical power by converting the energy of the observed photon into a measurable form. So what basically photodetector does is that it measures the photon flux. The operation of photoelectric detectors are based on the photoelectric effect, also called photoeffect. So what is basically photoelectric effect? It is when there is radiant energy on metal surfaces, electrons are emitted. So when electrons are emitted, this is called external photoelectric effect, and when the electrons leads to an photocurrent in that inside the metal, it is known as internal photoelectric effect. So this is basically the working device of photodetector. So we can see a metal surface here. This is an evacuated chamber. This is the positive terminal, and the radiant energy is this is anode, and the radiant energy is means incident on the photocathode. Then the electrons are generated, and it leads to a current, photocurrent, and there is a voltage source, and there is a current indicator to measure the photocurrent. So the absorption of photons by material causes electron to transition from higher level energy level, resulting in mobile charge carriers. As you have known, we have already discussed that this is called generation of electron and hole pair. Under the effect of an electric field, these carriers move and produce a measurable electric current. The photo effect can take two forms, as I have mentioned, that it is external and internal. External effect involves photoelectric emission, in which the photogenerated electron escape from the material as free electrons. The internal photo effect involves photoconductivity. This is the two terms are here important: photoelectric emission and photoconductivity. In external, there is photoelectric emission. In internal, there is photoconductivity, in which the excited carriers remain within the material and serve to increase its conductivity. The photodetectors are based on photoelectric emission and take form in the vacuum tubes called vacuum photodiodes or phototubes. So this is basically an example of this is photodiode, and this is vacuum tubes, right? So this is a basic vacuum tube. So this is a photocathode, and it is maintained in negative, and this is positive. And when electrons are means the energy is radiant on this photocathode, the electrons are generated, and it leads to a current. And this figure is quite complicated because the current which is generated in this one is very low, so very low. So what we do is that we means incorporate some diodes, which leads to an cascade generation of means the cascade generation of the electron, and the electrons are multiplied in each diodes. So this leads to a very good current or measurable current, and that's why we use diodes. And this is here a photocathode. We means we will go deep into that in the next slide. So there is incident photons, and there is a generation of electron and hole pair, and it is already always the negative means reverse bias to collect the electron and hole pairs. So in this slide, we will discuss the quantum efficiency and responsivity of a photodiode. So what is the basic definition of the quantum efficiency? That it is given as number of electron hole pair generated and collected divided by number of incident photons. So all the incident photons doesn't create electron hole pair. So the ratio of the number of electron and hole pair generated divided by number of incident photon can be called as quantum efficiency. So how we can find the number of electron hole pair generated? It is given by photocurrent divided by charge of electron. And number of incident photon can be found out by total power incident divided by power of each incident photon. So this formula also can be used to find out quantum efficiency. So now IP, the photocurrent is given by responsivity into power. So this is one of the important formula to remember. So this phi is flux, and we use this formula. The flux formula is given by means power divided by means energy of an individual photon, and this term eta E upon h nu can be termed as responsivity, and it is a new term. The responsivity is the means we can define responsivity as IP divided by ratio power. So this term is this responsivity can be different for different photocathode, and the simple formula by putting the value of E H, and we can find out that responsivity is equal to eta quantum efficiency into lambda naught divided by 1.24, and its unit is ampere per watt because it is current by power. And if there is gain in photo there, so the gain is sometimes there is avalanche photo there. So in avalanche photo diode, there photocathode uh, there will be a gain factor, and in that case the responsivity is multiplied by factor G. This will be a new chapter, and it is based on optical modulation. So optical modulation is the basically modulation of intensity, phase, and polarization and wavelength of the light. And the modulation basically means manipulation of these terms which I have mentioned. So optical modulator can be divided into two type of modulator: absorptive modulator, then refractive modulator. Refractive modulator is again divided into acoustic modulator and electro-optic modulator. And in electro-optic modulator, we'll discuss phase modulation, amplitude modulation, and polarization. So basically, we'll more focused on this refractive modulation part here. And here, the first one we are going to discuss in refractive modulation is acoustic effect. So refractive index of a medium can means in acoustic effect. What is basically it is defines that the refractive index of a medium can be altered by sound. It affects its optical properties. Sound is a dynamic strain involving molecular vibration that take form of the waves, which travel at a velocity characteristic of the medium. Therefore, we can say that in acoustic optics effect, sound controls light, and relationship between sound and light is given by the Bragg condition. So, what basically these lines say in simple terms that the sound affects the molecular structure of a material. So, what it makes that it makes them some denser regions and some rarer regions. These regions are denser and these regions are rarer. So by this affects the refractive index. Means those regions which are denser, they have more refractive index than those regions are which are rarer. So the light which is incident on this type of material which is manipulated by this sound is basically transmitted and diffracted, and this sine theta and the relationship between uh, this wavelength of the light and the wavelength of the sound which is manipulating it is given by the Bragg's condition, and it is given by sine theta equal to lambda divided by 2. We can say this eta dash, and this basically in Bragg's condition we know the basic Bragg condition formula is 2t sine theta equal to n lambda. This is for constructive interference n lambda, where here lambda is the wavelength of the light, and here d here is the wavelength of the sound which is manipulating the wavelength of the means which is manipulating the light. So this is basically the basic Bragg's law, and from here we are getting this sine theta equal to for n equal to 1 lambda by 2 eta dash. So that is basically acoustic effect. So in a nutshell, acoustic optics effect, you are using the sound to manipulate the light, and how we are doing this? The sound affect the refractive index of the material in which light is being incident by making compression and rarefactions. And in this slide, we'll discuss about we discussed once slide, and we'll discuss the other slide that is called electro-optic effect. In electro-optic effect, we are using electric field to manipulate the refractive index. So this the electro-optic effect can be divided into two effect, that is Kerr effect and Pockel's effect. So this is basically the setup, that there is a electro-optic material and that we apply the electric field and it affects the light. So when the refractive index as a function of electric field varies linearly, this is known as Pockel's effect. This these terms are important. Pockel's effect. Pockel's effect. And when the refractive index is varies to the power e square, this is known as Kerr's effect. Kerr's effect. So these two terms are important. You should remember that this is Pockel's effect and this is Kerr's effect. And in this, the refractive index is varying linearly, and this refractive index is varying quadratically with electric field. The another one is, as you have discussed, there are three parts in electro-optic effect. This one is the phase modulation in an interferometer. This is basically a Magenta interferometer. Magenta interferometer. So there are two branch one and branch two, and in branch two we are applying an electric field, and this electric field is how we are basically, in this case what we are doing is we are using the phase modulation to affect the intensity of the light. So while this is II is the means the incident intensity, and as there is two branch here, there will be, they are divided into I by 2 and I by 2, means II by 2. And in this case, this application of this electric field will lead to an a cos phi terms will be, a phase term will be introduced in this branch 2, and when these two are added, that will lead to half II plus half II cos phi, and this will simplify it as II cos square phi by 2. So the intensity is manipulated by this phase, and this is known as phase modulation, or we can say it as the intensity modulation. So the last modulator we should discuss is the electro-absorption modulator. So in electro-absorption modulation, the band gap energy of the material is reduced when an electric field is on. So what happens is that this electric field affects the band gap. So if this is that the band gap is HV1, it shrinks to HV2 or H nu 2. So it shifts the absorption spectrum towards the longer wavelengths. This phenomenon is also known as Frank-Eldas effect. So what basically happens is that if the absorption is taking place at lower wavelengths, means higher energy, this electro absorption means by applying the electric field, we are sinking it to lower wavelengths. So basically what happens is that now the absorption can take place at lower energy. So this is basically, this concludes the modulation part, and in this we have discussed the acoustic effect, the then Pockel's effect, Kerr's effect, and then our Magenta interferometer as intensity modulator, and the last one is the electro absorption modulator. So in the next slides we will discuss about the nonlinear optics. So the last chapter of the photonics is nonlinear optics, and we'll discuss this in brief. So basically, linear optics, what we do in linear optics is that in linear optics, which is also known as optics of weak light, light is deflected, delayed, attenuated, but its frequency or wavelength is unchanged. So one thing we have to mark here is that its frequency or wavelength is unchanged. Rest others can be modulated or changed. In nonlinear optics, which is also known as the optics of intense light, the light frequency is also get affected. So in nonlinear optics, there will be a change in the light frequency. This nonlinearity is typically only observed at very high light intensities. Values of electric field comparable to the interatomic electric field is typically 10 per 8 volt per meter. So this nonlinearity is only observed at when we are applying an electric field which is comparable to an interatomic electric fields, which is typically 10 to the power 8 volt per meter. So this is very high. such as those provided by the pulse lasers. So what basically here is happening is that these are two input light photon energy, and these two inputs are then when there is emission, these two inputs are converted into one output, and this is the color of this output will be different means the input, if the input is red, and these two inputs are together mixing to get giving rise to an higher wavelength, and this is and that's color is blue, and the color can be anything, means blue, violet, anything. So basically what happens is that there is a input wave, and this is a molecule, and if we are giving one color, we are getting another color, so that means the frequency or the wavelength is affected in nonlinear optics. This is the fundamental view of nonlinear optics, that in this polarization, the term polarization is not linear as you have studied. So in this case, the polarization is varies as means E square and E cube. So on the basis of that, we are discussing chi1 process, and chi2 process is known as in which the polarization varies as E square. This is known as second harmonic generation, and chi3 process in which polarization is varies as electric field cube. This is known as the third harmonic generation. So in first harmonic generation, this is linear optics. So omega 1, if the light frequency is omega is observed, then the emitted is also have the frequency omega. In chi2 process, two photons are observed, omega 1 and omega 2, and one single photon is of omega 2 is being released, and here in this case omega 2 will be equal to 2 omega 1. This is called chi2 process. And in chi3 process, there will be three photons, and omega 3 will be released, and this is known as third harmonic generation. And if we draw the curve of P versus E, this will be linear. P1 is linear, P2 will be the second harmonic generation is quadratic in nature, and the third harmonic generation will be cubic in nature. So the last part of the nonlinear optics is the Raman and Brillouin scattering. So there are two types of scattering in elastic scattering, that is known as the Rayleigh scattering. If h nu is incident, we are getting h nu back, which is the energy is typically conserved. So this is known as the elastic scattering. And in non-elastic scattering, we know the word non-elastic means the energy will not be conserved. So if h nu frequency is incident, the new frequency will be h nu dash, and this is known as Raman and Brillouin scattering. So the most important difference between Raman and Brillouin scattering, that in Raman scattering, that is the Raman scattering is due to the molecular when the light is interacting with the molecular vibrations, and in Brillouin scattering, the light is interacting with the lattice vibration. So that's the difference between Raman and Brillouin scattering. That in Raman scattering, there is the interaction of light with molecular vibrations, and in Brillouin scattering, it is the interaction of light is with the lattice vibration, or that lattice vibrations is known also the acoustic phonons. And in Raman and Brillouin, in both the cases, we'll get Rayleigh line, Stokes line, and anti-Stokes line. So the Rayleigh line will be the same frequency V naught. So if we are incidenting an frequency of V naught, we'll get another the Rayleigh line will be the elastic scattering line, and it will be the wavelength of the light emitted will be again V naught. The anti-Stokes line will increase the frequency by delta V, and the Stokes line will decrease the in anti-Stokes shift it will be increased by delta V, and in Stokes shift it will be decreased by delta V. So this is basically the diagram of energy diagram of Stokes Raman, Rayleigh, and anti-Stokes Raman. Same goes for the Brillouin. There will be Stokes Brillouin and anti-Stokes Brillouin. So this basically concludes all the lectures of the photonics. Thank you all for being here. So basically, we studied the entire photonics. We covered the entire photonics in a brief manner. And I think the study of light is very, very important, because when Einstein gave the special theory of relativity, he just in his second first one is the laws of physics are invariant, and the second one is irrespective of the light source, the speed of light is always constant, and that changed the entire physics, entire classical physics, and it affected everything. So that's why I think this is one enough reason we should be interested in the study of light or photonics. So basically, this concludes all my lecture. Thank you.